Okay, sorry, for a bit of a delay. Next talk will be by Mohammed from Suze, and he will talk. Sorry, okay. I haven't said anything. And he will speak about cost effective AI inference. So the stage is yours.
Thank you. Yeah, so thank you for being here today. We will discuss how we can do cost-effective AI inference, outside of that frontier AI lab world and hyperscalers. So a little bit about me. My name is Mohammed Belgaid Hassin. I'm at Mirantis, and for somehow the logo here is not showing correctly, but you will excuse me for that. I'm the original creator of 3 cluster API providers. Some of them now have been taken over by other teams, but yeah, so these are CAP RKE2, CAP HV, which is for Harvester, and CAPOX, which is for an infrastructure provider for Oxide. At my company, I help customers implement cloud-native solutions, and my focus with them is around, infrastructure abstraction. Good. So today, I will give you first a role of a chief data officer at a hospital, okay? And we'll see what kind of problems you might have. So your boss comes to you and tells you, I need an AI strategy. His motivation is that his hospital is understaffed, and the doctors and medical staff are overwhelmed by administrative tasks and a lot of things to do, and there are a lot of patients, etc. And he thinks that he's hearing AI here, AI there, and he says this thing should at least help me lift up a little bit of the burden of my doctor's shoulders. So and when you hear him, you actually agree a little bit because you heard about different healthcare use cases for AI inference, such as structuring messy medical notes or anonymizing data for usage for research, for example, or assistance with diagnosis. However, the data that you have in hand is not easy to handle. It's really sensitive. It's not only personal data, but it's health data. So you have to have compliance with things like GDPR and HIPAA and etc. So because of that, the public cloud or public AI inference endpoints become really a no-go. You cannot just trust, public services. You need to have something that is on-premise. So you go and look for on-premise solutions, okay? The problem is you find 2 extremes, at least if you just follow, what you hear, what you see, like these headlines and stuff, whatever you can see in the, for example, on KubeCon main stage or something. So first of all, you will see production-grade AI deployments, and frameworks, but these are mostly built for data center scale infrastructure. So I'm thinking about GB300 clusters, huge machines that, or huge racks that would cost millions at a time. And this is what basically makes the headlines these days. And on the other hand, you see hobbyists that are making really wonders with consumer GPUs, sometimes single GPUs, or in this particular case, maybe a couple of them. But they are doing things that are interesting. The only problem is that it's not resilient, it's not observable, and it cannot be used in production. And I do think that most of enterprises will live in the middle, between these 2 worlds. That means that at the same time, they cannot afford the huge GB300 clusters, and on the other hand, they need the same approach for production-ready deployments that will make we make them able to operate securely this infrastructure or these services. So the rest is actually these people is the rest of us. Okay, maybe not all of us need this or have very strict requirements about having data on premise, but we have also that idea of maybe being more independent from cloud providers or AI frontier labs. Anyway, if you focus again on that chief data officer of the hospital, it's just an example, because outside of that, there are a lot of enterprises that have exactly the same kind of profile in terms of requirements. We have government agencies, we have financial institutions, we have legal firms, we have manufacturing companies that want to preserve their intellectual property, and many more, insurance, energy, telecom, whatever. So the pattern is always the same. All these enterprises have AI use cases that they want to deploy. However, they all have a reason to not let their data go away, go to the public cloud, go to AI inference provided by online endpoints. Okay, so here the photos are. So the rest of us, what do we all have in common? First of all, budget. We cannot buy the GPU farms that I mentioned before. These cost really millions. And the AI budget for most of enterprises is just a corner in the IT budget overall. It's not something that you can put a lot of money into. If you look at the team sizes, these are usually also pretty small, at least in comparison. You might have maybe 2 people, maybe up to 5, managing a Kubernetes platform, maybe a platform team. But you do not have this extensive machine learning teams creating new models and fine-tuning existing models, et cetera, et cetera. And this is backed by recent research. For example, in a 2026 research from DigitalOcean, their results show that 44% of enterprises that put money into AI, they put 75% to 100% of the budget into AI inference only. So basically, they just handle inference as another workload in an existing environment. Okay? And this existing environment is mostly Kubernetes, or at least in this room here, you probably use Kubernetes for deploying various types of workloads. And you're wondering, can I do the same thing with AI if AI needs this huge compute requirement to achieve simple use cases? Well, let's take a step back and continue our research into how can we answer this challenge. And now we remember our hobbyist. We said that on one extreme end, there is this hobbyist who is tinkering with his GPU rig, and he's doing wonders. So the question is, why? Why is he able to do wonders? And the answer is open weight models. If you take a look at, I don't know if everybody here is comfortable with AI jargon, such as open weight models. So open weight is the equivalent of open source, very vaguely, in terms of AI models. These are models that are available to download, to use, and to modify on specific platforms, and they have gained a lot in intelligence and capability in the last year or so. For example, a model that can run on a very simple consumer-grade GPU, such as an RTX 4090 with 24 gigabits of RAM, today handily beats a frontier model from around 1.5 years ago in many metrics. So open-weight models have become really, really capable. And they're come in different sizes and need different levels of infrastructure. But many of those that you can deploy on simple consumer hardware are already capable of answering a lot of use cases. These use cases can be RAG and internal document and knowledge-based analysis. It could be structured data extraction from messy text and notes and whatever. It could be document summarization and profound analysis, or OCR, for example. A very simple use case for AI today can be just taking huge amounts of written notes and paper documents and digitize all of that, put it into databases, and make it more structured and more useful. And also, and probably all of you know about this today here, things like code assistance or agentic AI. All of these use cases are today possible with on-premise, self-hosted, open-weight models that run on very commodity hardware. Okay, so let's summarize our situation. We know that the demand for AI is real. They are useful use cases that many enterprises want to at least test and implement. The use cases that they see should provide value. There are capable models that exist out there. And these are, there is also cost-effective and good enough compute to make this work. So what's missing? We talked about, that hobbyist. So what's missing? What's missing is a production-grade tooling to run inference in production on modest and also heterogeneous hardware, because you might have, GPUs of different types and stuff. Or is it actually? So we mentioned that, the rest of us, this middle ground, already probably has, teams that know about Kubernetes and deploying workloads in production and stuff like that. What if we use most of these, but maybe with a small twist? Let us give it specifically AI inference superpowers. So this cheeky sentence, you might already think about, an agent that goes into Kubernetes and does stuff. No, actually, that's not what I'm thinking about. I'm thinking about here a number of projects, CNCF projects that exist already that answer these challenges for you. The first of them is at the infrastructure level. You will probably not be driving a small rig with 3 or 4 GPUs, right? You will have way more users than this hobbyist who probably has 1 user. You need something to scale, and you need a lot to monitor, to control. You need this resilience that in Kubernetes, et cetera. And at the infrastructure level, the scalability thing can be given by Cluster API. But today I'd like to show you 3 additional CNCF sandbox projects that can help you continue being more efficient, specifically cost efficient with Kubernetes end-to-end GPUs. One of them is HAMi. I don't know if how many of you know about Project HAMi? Yeah, a couple of already. So for all the rest, I hope I can give you some new information today. So HAMi is about GPU sharing and abstraction. Okay, and I will talk a little bit more about it in a second. Then the second project is Kaito. Kaito is a project that handles language model lifecycle as a CRD. So it simplifies deploying large language models in your infrastructure. And LLM-d is for advanced LLM routing for traffic. You probably know about Cluster API already, so I will not spend too much time on this slide. But the idea is that it can provision infrastructure for you, any type of infrastructure. It could be, in this case, for on-premise, it would be hypervisors such as VMware, Nutanix, bare metal, you name it. And it will manage the cluster life cycles. That means that if you lose a node for some reason, it will respin a node to replace it. It is a sort of pluggable auto-scaling mechanism that you can use Cluster API to handle the infrastructure that is requested by an autoscaler. And that way you achieve something quite similar to what public clouds can achieve. So at the same time, it is useful both on-premise and in the cloud if you do have that use case. If you talk a little bit more about HAMi now. So HAMi's idea is that we should avoid having a vendor such as NVIDIA completely control the GPU AI inference space. We should be able to work with any type of accelerator, and in this case, we're not only talking about GPUs, any accelerator for AI inference. So it abstracts the way that deployments on Kubernetes will call out the accelerators so that you don't specifically depend on NVIDIA, you don't specifically need data center grade GPUs of NVIDIA. You can use consumer ones if you want to. And also, you can share these GPUs. You can slice them and use them accordingly. So that's the most important features of HAMi. That way, you can maximize utilization of your GPUs, especially if you use small models compared to the capability of your GPUs. If you have GPUs that have a lot of RAM, for example, and a lot of compute, then smaller models might not use up all the capabilities or capacities of these GPUs. So you need to do GPU sharing, like running on one GPU, multiple models or something like that. Now, Kaito. Kaito is like the problem that you have today is that, or that you had before Kaito, was that deploying a model on Kubernetes, meaning that you need to put together multiple things that need to interact correctly, like a VLLM to do the actual inference, choose the right version of VLLM for the right GPU, and which CUDA version, and figure out how you run this VLLM correctly, and how do you configure the rest of the components, such as config maps and services and secrets and stuff like that. So it abstracts all of that for you. In Kaito, you deploy one CRD called Workspace that will handle for you the deployment of the inferencing pod, downloading of the right model, as well as continue to handle like service endpoints, etc., for your pod. So it simplifies specific AI inferencing workloads on Kubernetes. You can see it as the deployment for AI inference. And finally, LLM-d, which is routing that understands LLMs. So in this case, LLMs have very specific needs. For example, for latency, you need to send um, in a chat history, for example, you need to send the subsequent chat to the right instance because there's something called the KV cache, which maintains the chat context. And if the KV cache is not on the right instance, it takes time to just get it over from some other place, and that's not very useful. If you want low latency, you need to route to the right pod that has the right context in the VRAM. Anyway, so this is just, LLM-d has a lot of features, but this is the most interesting feature, I think, which is, intelligent load balancing, KV cache management, and handling, and latency-based routing. Now, the 4 projects I mentioned actually work better together if you look at them as a whole. So you have Cluster API that enforces just-in-time infrastructure and elasticity. You have HAMi that maximizes efficiency and utilization of your GPUs. You have Kaito that simplifies deployment of models. And you have LLM-d that handles the right routing. I need to go a little bit faster. However, we need to also not forget that we have people that know about Kubernetes, that they want to see the same thing, and we need to reuse this knowledge. And that's also the case in Kubernetes because we have the rest of production readiness with Kubernetes that is with the resilience, observability, governance, and security of Kubernetes, business as usual in Kubernetes. Let me go through these slides relatively fast. Resilience can be handled by Kubernetes itself as an orchestration platform, but also by Cluster API at the infrastructure level, Kaito and LLM-d for the higher levels, like Kaito for the model management and LLM-d for the routing. Then observability. Alerting and monitoring dashboards, solutions like Prometheus and Grafana are also useful with AI inference. There are GPU metric exporters that exist for nearly all of the GPU vendors. NVIDIA has their own, and AMD has an equivalent, and Intel has also an equivalent. So these can be plugged into the existing monitoring solutions to expose the GPU metrics. And then you have distributed tracing to analyze each individual request. Which path did it take in your infrastructure, and how, and maybe do some troubleshooting on top of it. What is already the case for web services and stuff. And naturally, you have centralized logs and audit. Then you have governance through admission control. This is also relevant for AI inference, which team can do what and deploy which model and this kind of stuff. Quota management, because GPU is a rare resource and it's important to manage quotas. Tenant isolation, you might have multiple teams that should not communicate together, so their workloads should not be the same. All of these things, you are already used to them, and now you just need to extend slightly Kubernetes to make this possible on with AI inference. And finally, security, with everything that you know about network policies, secret management, certificate management, etc., etc. You have also other ways, naturally, that already exist, like doing CI/CD through Argo CD and stuff, doing backups. All of that is part of Kubernetes that you hopefully already know. So if I need you today to have some takeaways, I mentioned this, the rest of us, the forgotten middle. the enterprises that do not have the budget for GPU clusters, but do not want to do tinker with stuff, but also do production grade. This is, in my opinion, the biggest part of our community, and it's growing very fast. As I mentioned about this 44% figure, and many predictions in the industry that says that GPU inference will be very broadly developed until 2030, and it will not cost that much, and it will oversize or be way more in terms of compute than training. For these people that want AI inference at low cost, Kubernetes already have them covered. HAMi for the GPU layer, Kaito, LLM-d, and all the rest that you already know helps doing this AI inference in a efficient and production-ready way. So I will ask you here to go ahead and give these new projects a little bit of love, use them, test them, create issues, and contribute if you can. So finally, what I will say is you don't need really hyperscalers or AI frontier labs to work with AI and have useful AI in your environments. Standard Kubernetes can do it, and 3 sandbox projects will help you with that. Thank you, and let's have our Q&A. Oh, sorry. Okay. So, yeah. So the question is, yeah. The question is, what types of slicing does HAMi offer? So HAMi actually supports multiple types of slicing. There is the HAMi slicing that is actually the equivalent of the vGPU approach in NVIDIA. It really intercepts the GPU calls and translates them, I would say. So it's really very close in terms of performance, etc., to native vGPU from NVIDIA. You might know, however, that vGPU in NVIDIA is not supported on all GPUs. It's actually designed more for data center grade GPUs, and that is actually licensed as well. So HAMi offers the possibility to avoid all of that and to do it for all types of GPUs, not only NVIDIA. It does support time slicing, and it can work in addition to time slicing or other types of partitioning. So, any projects to help with model training specifically? So, from not Sam Altman, very good. In this specific case, I really focused on AI inference because, in my opinion, I'm seeing the inference as being the majority workload in the near future. The rest of us. However, there are a lot of model training stuff that exists that is more on the Python part. The part where you have machine learning teams that work on improving models and stuff. If you're talking more specifically of how you handle infrastructure around training, then unfortunately I did not study enough to give you examples of what you should do. But I remember like there are a lot about big job handling, because training is more like a huge chunk of jobs at the same time that come for a period of time. So it's not originally designed for Kubernetes, but it can be useful through stuff like Slurm or other gang scheduling kinds of approaches. So the presentation mentioned observability, but how is remediation handled? GPUs are unstable. How is remediation? You mean if you see errors in GPUs, is that what I should understand here? So the GPU exporters will show you the metrics on GPUs as if it were normal CPUs. It's like load and like state and memory state and this kind of thing. So if I don't know why there is this affirmation that or declaration that GPUs are unstable, but GPUs are like CPUs, right? It's really compute, but it's done in a different manner, a more parallel way. So handling should be more or less similar in that you evaluate the load, you avoid having memory that is full, or this kind of approach. So I don't know what is exactly meant by that, but that's the answer that I can give. Is it possible to bypass NVIDIA CUDA nowadays? So again, I'm focusing my talk today on AI inference. And in AI inference, yes, absolutely. You can completely bypass NVIDIA. These many of these projects actually already suggest that NVIDIA is not the go-to solution for inference anymore. So we have things like Google TPUs, but also TPUs are also used for training, but Google TPUs, AMD GPUs, Intel GPUs. The stack today, which begins with kind of this inferencing pod that is VLLM, do absolutely work outside of CUDA. AMD has a solution called ROCm. Intel, I don't remember the name anymore, but there is also libraries and stuff around that. So, and VLLM is improving very fast to support these additional vendors as well. So yes, absolutely. I don't see any questions anymore. So thank you very much.
I want to point out the GPU unstability data. NVIDIA was preset the open source project for any safety now.
NV?
I have like sort of like an old problem detector.
Yes. There you are. Okay. So thank you very much. And wish you a very nice continuation.